a really unique opportunity to put ourselves in the future, but not just to imagine confronting it as we are today, to imagine confronting it as we will be. Big question about how that looks. That's the spirit of today, almost hindcasting from 2036 to imagine what actions did we take, what levers did we pull in order to build the resilience of Brisbane to cope with this inevitable recurring event. Around the world, things are happening, big things are happening. We see, for example, some images will pop up. In Japan, we have an extraordinary underground flood mitigation facility where kilometers and kilometers of storage are enabled. 200 tons of floodwater every second can pump into this. If we flick to the next one, we see that, and I'm sure that very shortly, Rotterdam, water city of the future. Imagine building a massive parking lot that's designed to flood in. 10,000 cubic meters of water can be pumped in half an hour and then pumped back out. Imagine designing something like that. If we think through Copenhagen's green roof policy, the first city in the world not just to mandate that we'll accumulate water on rooftops for many reasons, heat wave mitigation, but crucially flooding, will actually offer incentives for retrofitting the existing housing stock along the way. Very different world when we look at how we design it. And then, of course, suddenly we see the freeways that we built 20 or 30 years ago being reclaimed as rivers. And many may not realize that City of Melbourne fully intends to turn Elizabeth Street back into a creek. So how we think about what happens next, I think, let's use our imagination starting from where we are. We have a huge program today with some really amazing people, including you in the audience, and sadly, I've seen who you are. And I know that there's some incredible people here, and I fully intend to ask you questions along the way. So thank you very much for making yourselves available for this incredible event. Can we start by really understanding, through the eyes of the Bureau, Blair Trewin, if I can encourage you to join us. Blair's going to set up for us how the climate in this part of Australia looks in 2036. And against that background, we'll begin to imagine the scenario that we'll explore.
Okay, well, thanks for inviting me. And what I'll do is I'll run through some of the climate factors underlying the 2036 scenario, those things which we are reasonably confident are going to change, those things which we don't have a clear indication are going to change, and what aspects of natural variability are relevant, because something that I think is probably fairly poorly understood in the broader community is just how wide the range of possible variability is in this part of the world, even without any change in the underlying climate. Firstly, what happens between now and 2036 is already pretty much locked in. Obviously, there's been a lot of debate, well, for decades really, about what to do about greenhouse gas emissions. But at the timescale we're looking at, it doesn't really matter, because the lag time between a change in emissions pathway and a significant change in what that means for the climate is somewhere around 20 to 30 years, which is one of the many things which makes climate change such a challenging policy problem to deal with. And if we look, for example, at the difference between very high-end emission scenarios, which in IPCC language is RCP 8.5, that's for the red plume on these plots, and very low-range emission scenarios, which is RCP 2.6, we see that for a range of variables, those basically don't diverge until after 2040. So so whatever the sources of uncertainty in climate change projections between now and 2036, what happens to emissions is not really one of those. The uncertainties are much more about natural variability overlain on climate change, and also the uncertainties involved in climate modelling. Also, but as natural variability is very large. The next slide, please. And what I've got here is looking at the catchment average rainfall over the Brisbane River catchment for the wettest day of the year, each year from 1900 through to 2015. And you can see there's an enormous amount of variability there. You've got the highest value there is 171 millimetres. That was the 1974 flood. But you have years where it's just under 30 millimetres, the wettest day of the year. So you've got a very big range there between wet and dry years. You don't have much of an observable trend in that. If you run a fairly simple straight trend line through it, you get an increase of about 10% over the century. But if you take out the last 8 years, which have all been reasonably high, you've got basically zero trend. And one of the things about extreme rainfall time series is because there is so much variability, it's very hard to say convincingly, yes, we do have a trend in this, because even a 20 or 30% upward trend probably isn't going to show up as statistically significant amongst all the year-to-year variability. An event you'll hear a little bit about, I think at some points today, is the 1893 event, which for Brisbane was a much higher flood event than 1974. Our gridded rainfall analyses, which we've run this plot off, only go back to 1900. But looking at those individual sites where we have data from 1893, on a catchment-wide basis, 1893 was probably fairly similar to 1974. But one thing that 1893 had was it had a pocket of phenomenally heavy rainfalls concentrated in the northernmost part of the catchment, up around the back of the Sunshine Coast and Glasshouse Mountains. You had places up there that were getting up to 1,400 millimetres in 2 days, and you can just imagine how much water that sends down for relevant catchments. Okay, so next slide, please. So the lot... in 2036, many of the fundamentals of Brisbane's climate will still look much the same. It's still going to be a climate where rainfall peaks in the January to March period, and that's going to be the time of year when the highest flood risk exists. Some of those very heavy rainfall events I showed on the previous slide were actually well outside that window. For example, the third heaviest daily rainfall on record in the Brisbane catchment was actually a July event in 1965. But those out-of-season events, generally speaking, aren't associated with really big floods because they're falling on drier catchments. That can apply to in-season events as well, and you only need to look at the comparison between the 2011 and 2013 events for that. The catchment rainfalls for those two events were basically identical, but 2013 falling on catchments which had 50 millimetres of rain in the last month and not 500. The basic weather systems that drive extreme rainfall are probably going to be reasonably similar. Sometimes easterly troughs, sometimes tropical or subtropical lows. We're not suddenly going to start getting Category 4 or 5 cyclones in Brisbane every second year. The risk of getting a full-blown cyclone into Brisbane is always there, but it's a fairly rare event, and it's probably not going to become significantly more likely over the next 20 years. As an aside there have been some changes over time in what we think of as being a tropical versus subtropical cyclone, and Cyclone Wanda in 1974 probably wouldn't be named as a cyclone if it happened today. It'd be considered a subtropical system. And something that's also certainly going to be still with us in 2036 is there's going to be a lot of variability from year to year in climate, and particularly in rainfall. Next slide, please. So there are some variables where we can be quite confident in the direction of changes, not necessarily for magnitude. And the most obvious variable there is temperature, which is basically not terribly relevant to a flood scenario, but I thought I'd put it up anyway just to illustrate where we do have confidence. You can see on the plots on the left that under all scenarios there's a reasonably substantial temperature rise. Model projections indicate a rise compared with 1986 to 2005, which is the baseline period for the projections I'll show here. An increase of somewhere between 0.4 and 1.3 degrees in this part of the world. Looking at the geographic patterns of warming, the slide I've got up are for 2090 because that shows the geographic patterns better, but in earlier times the geographic pattern looks similar, it's just the magnitude's less. And what we get out of this is that compared with the national average, southeast Queensland is the amount of warming in southeast Queensland is likely to be fairly similar to the national average. Areas of the interior are likely to have more warming than the national average, and areas close to the southern coastline less. That's largely because the more continental climates are, the more they're likely to warm, and conversely the Southern Ocean is expected to warm the least of any part of the world, so areas that have exposure to that will see less warming. Next one, please. Rainfall changes much more uncertain, and this is showing the range of model projections for a variety of time periods and for 4 seasons. For what in the Climate Change of Australia report is called the East Coast North subcluster. That's basically integrated over a region from the New South Wales border up as far as about Rockhampton, but can be considered as broadly representative of this region. So when we're looking at total rainfall, climate models suggest not a particularly strong signal in summer and autumn, but models lean quite strongly towards a drying signal in winter and spring, and probably not quite so significant to a flood scenario, except perhaps in as much as it might influence things like what the status of water storages is coming into summer. But for rainfall's a lot harder to model than temperature is, and the range of possibilities is quite large. Next slide, please. But what we see is, even against a backdrop where the most likely scenarios for rainfall to stay stable or decline in total, we still do see models leaning towards increases in extreme rainfall, although again with very wide levels of uncertainty. The mid-range of model estimates is indicating an increase of around about 5 to 10% in the variable they looked at, which is the value of the estimated wettest day in 20 years at a given point. But you can see there that the range of possible outcomes is big, and there's potential for surprises along the way. There has been other work looking at the issue from a slightly different angle, looking in more at specific regions such as the Gold Coast hinterland, for example, which suggests a slightly stronger signal than that. But I think the general message here is that the odds probably lean slightly towards an increase rather than a decrease in the risk of extreme rainfall events, notwithstanding the potential for a decline in average rainfall. But at the 2036 timescale, we're probably not talking particularly huge numbers. Next one, please. But even a fairly modest increase in extreme rainfalls can actually have quite a large impact on the frequency with which a particular threshold is breached. And what I've done here is I've plotted the one-day catchment average rainfall for the Brisbane River catchment against its frequency in the historic record. So on the right, the blue dot on the right, that's the wettest event in the record, so once in 116 years of observed history. Then the second one is twice in 116 years, and so on. And then the red dots, I've stated a hypothetical 10% to all of those. And what we see there, if we compare where that curve sits with historical observed values and where a curve 10% higher sits, is that the frequency of which you breach a certain threshold, say 150 millimetres, can go up by a lot more than 10% for a 10% increase in the rainfall amounts. At some thresholds, you're potentially looking at an increase in frequency of 50% or more. That's a factor of a relatively modest increase in the absolute numbers causing a big increase in the frequency of a threshold breach. Depending on the local geography, that can apply even more for sea level rise. And that brings me on to the next slide. So probably the final part of the climate picture is what's likely to happen with sea level rise. And this is another area where we have a high level of confidence in the change that we're likely to see. We'd expect to see changes in the order of 10 centimetres relative to 2011 by 2036, and about 20 centimetres relative to 1974. In the context of a major flood, that clearly influences things like how effectively the lower reaches of the river drain, quite apart from any issues with coastal inundation. But I think it also needs to be remembered that there's quite, even sea level rise, people tend to think of as being fairly monolithic. But even with sea level rise, there's quite a lot of interannual variability overlaid on that, and in particular during strong La Nina events, sea levels along the east coast of Australia can be 10 centimetres or more above baseline, essentially as a result of stronger easterly winds through the Pacific pushing water from the east side of the Pacific to the west, in very crude terms. And because major floods in southeast Queensland are more likely to happen during La Nina years, that aspect of variability potentially can exacerbate the situation. And of course, on top of that, depending on the exact weather system that's causing the floods, you might have a significant storm surge factor as well. Although something that works in our favour with a relatively large catchment is that by the time the flood peak reaches the lower Brisbane River under most scenarios, the actual weather system driving the floods is probably going to have moved on. So you probably have some separation in time between peak storm surge and peak river flood. In smaller catchments, that may not necessarily be the case. So I think I'll finish up there and open things up to Mara to take it from here.
Okay, so please, if you have questions of Blair, I'll encourage him to stand up here for another 5 minutes or so. And as you gather your thoughts, I can't help but ask one question. So take yourselves back to that 1893 event. If you want to get your head around it, go to hardenup.org and find 1893. There's a great case study by the Bureau on that website. And just reflect on the work, for example, of Professor John Knott up in James Cook University in Cairns, who suggests, through an article recently republished in Nature, that actually the 20th century may have been a relatively quiet severe weather period, and the big events of the 1800s may indicate more of a meta cycle around that. So Blair, help us to get our heads around this variability that happens within the cycles of major weathers, especially here in southeast Queensland.
Yeah, well, when you're dealing with extremes, sometimes a century of information is not enough to give you exposure to the full range of extremes. And one of the rules of thumb I have is if it has happened before, it can happen again. And we know that it is possible to get 1,400 millimetres in 2 days in southeast Queensland because in 1893 it happened. And if it happens again, it won't necessarily be where it happened last time. It might be, it might be in metropolitan Brisbane. It might be on the Gold Coast. And when you're looking at, perhaps trying to quantify, what might be a 1 in 500 or 1 in 1,000 year event, you're dealing with very, very, very wide ranges of uncertainty. Even under natural variability, even without adding climate change into the mix.
Thanks for that. Are there any questions for Blair from the audience? We are running a little bit behind, so that may be a godsend. I think we are okay. Thank you so much, Blair. Really appreciate your contribution.